Most wonderful good morning. Good morning. Most wonderful good morning.
How are you?
I'm very well, thank you. And your good self?
I'm good, thank you.
Morning. Good morning. Good morning. Good morning.
Oh yeah. I think they're external. Actually,
A most wonderful good morning. Good morning. Good morning.
yeah, it was kind of choreographic. I think.
Good morning. A most wonderful good morning. Good morning. Good morning. Most wonderful good morning. A most wonderful good morning. Good morning. Good morning. Good morning. Good morning. exactly how I feel. I want to go to sleep.
I will try my very best. If I will try not to, but it's not your fault.
Even if it is my fault, I don't care.
Okay. Also, sir, I would like to say it is so annoying. When I saw that message that you'd got a complaint about you not replying to messages on Messenger.
Yeah, I saw that.
I was like, are you joking? Because the amount of stupid questions on there, that if they literally just had the time to look through, they would find the answer. I was like, rubbish.
Mainly so I don't keep.
You are literally the most helpful lecturer.
Thank you very much. It's very kind of you, but
I did read it and I was like,
I don't know, because loads of people ask me about things.
it is an opinion. I have to accept it. It was suggested to me by some colleagues of mine to basically say I'm not supporting the group chat anymore. And my take on that is everybody is entitled to their own opinion, and it's fair enough.
It's just Bailey and how to
But I don't do any sort of. I believe that the group chat is helpful for students.
and it is, because it's like most of the time people can come to their own conclusions and it's healthy, but like you're literally
Bullshit that someone complaining
so
about.
annoying. Like it actually annoys me.
No. It's not worth fighting.
It's like,
No, it really pisses me off.
Let's not get worked up. Sorry?
it's not your fault. We're not.
Thank you. It's very kind of you. Right, let's make a start. Most wonderful good morning, everybody. And welcome to sort of a new chapter where we do some hardcore metabolism. Before I get started, please do the attendance thingy on your devices, Moodle. You know how it works. Also, you probably have noticed that all quizzes, BI 301 and BI 308, are open again. So if you haven't done the previous ones, do them. If you have done them, you don't need to do them again. Obviously, it should all be recorded. Please do check on the respective website that your login is present on the score sheets. If it's not present, then I can't see it, right? And if I can't see it, I can't count. If it's not present, I mean, a student emailed me and said, I know that I have done it, but it's not on the score list. Should I redo the test or the quiz? Well, obviously, because if I can't see it, what do you want me to do, right? But if you have done it and if you're happy with your score, you don't need to do anything, right? So that's that bit. Resources. I think I've emailed you with some very useful resources for metabolism. My predecessor, the colleague who did this part of the module last year, handed over all his slides to me. And they are also available on Moodle. So in theory, you don't need to buy a lot of new textbooks or anything like that. Please make use of these slides. By the way, the session for today, according to my colleague Rokas, amounts to 100 slides. I would advise not to download and print them, unless you want to, reinvent a textbook. By the way, this here, Leninger, is a useful textbook, and it basically, it has far more information on it than you will ever need. And just as a sort of a reference, but it's not the only textbook. Biochemical metabolic pathways haven't changed in the last 50 years, at least not to my knowledge. And what we are doing in the first year is nicely covered by a lot of textbooks. There is even, and I think I sent out the link to the free version of Stryer. I have a very special relationship to Stryer because that was the textbook that I used when I learned biochemistry. So I love it. You can't, my understanding is you can't download the textbook, but if you go to the link, you can put in the search bar, search items, and it comes up with the chapters. And I think it's really nice and useful. What do I expect people to know for quizzes for the rest of your life? We will discuss some metabolic reactions. And I would really like you to know the name of some specific enzymes. And we'll point out which enzymes I want you to remember. But because you can all look up in textbooks, I would probably not necessarily ask you in detail about structures of the different metabolites. There will be some metabolites that you inevitably will learn. So for example, pyruvate, you will need to know what the structure of that thing is. But if we are talking about more complex things, then I'm not going to ask you that. Because it's not about memorization, it is about understanding what's actually happening. And as I said, I'm not too fussed about the different reactions, how they proceed and things like that. I am more interested in how things integrate, how things are regulated. And I want to show you that things, that reactions usually make sense. Not always, but usually they make sense. Okay? Happy with that? So, I'm not going to show you 100 slides. Thank you very much. This just, I can't cope with that. So, it is really back to the drawing board. And, well, just a sort of want you to do something for me now. If you can, and if it doesn't cause you any pain, if it is painful for you, don't do it. But what I want you to do is stand up, please. If you can. And now, what we are going to do is, if you can, if you can't do it, please don't do it. I don't want anyone to be in pain, to pass out, to keel over, or to start vomiting and things like that, right? What I want you to do is arms in front. I would usually open the window, and I want you to do this. Up and down, and up and down, and up and down. Ben, come on. Oh, fuff. Up and down, right? Lovely to see that. Thank you very much. You all survived it? That's a great thing. So, what is actually happening in your body, in your muscles, when you did this exercise? So what's happening? What's going on in the muscle? Obviously, you are doing some work. You're doing exercise, right? And for any kind of work, any kind of exercise, we need energy. Be it hockey, be it rowing, be it running. Do we have any avid runners here? Sprinters? Yeah? Excellent. What's the record? 100 meters.
For women or men?
Yes.
Which one? Men is 9.58, women is 10.49.
So around 10 seconds per 100 meters. Can you do that? Are you close?
My 100 meters isn't so good, my 200 meters is good.
Oh, okay. Oh, we come. So you need energy because your muscles do work. Your muscles do mechanical work. You know about the sliding filament theory, where the actin and myosin filaments slide along each other. And that is mechanical work, but also the muscle contracts and basically lifts your body up or propels it forward. So what kind of energy do we feed into this process? What's the general energy currency that every cell uses? Yeah? ATP, exactly. Be careful, certain dialects in the UK and across the world, it's really, really difficult because they talk about ADB and ADB. And you have no idea what are they talking about, especially when you have a cold. So you're talking about ADB. We are talking about ATP, adenosine triphosphate. And that is the general currency. So, when we do exercise, we use ATP in the cell for the muscle to do something. That means we have a pool of ATP present. How long do you think does this pool of ATP actually last us? Have you done that before? No? How long do you think this pool of ATP that is in the muscle cell, we're currently talking only about muscle cells, how long does this pool of ATP last? Have a guess. Hours? Days? Where are the sports people? Emily? A few seconds? Nice one. Actually, the pool of ATP that you have only lasts for about 5 to 6 seconds. And it's not just the ATP, you also have a compound in your muscle cells. This is called phosphocreatine. This phosphocreatine takes ADP and converts it into ATP plus creatine. And the enzyme that does that transfers a phosphate and therefore is called creatine kinase. Remember, a kinase is something that transfers phosphate. And then we can use the ATP that is generated to do work, but that only lasts us about 5 to, let's say, 7 seconds. Even in the best trained sports people, you have 5 to 7 seconds ATP resource. But, Lizzie said, for a sprint, even a 100-meter sprint, where we are in the range of 10 seconds, the ATP pool is not sufficient. These 5 to 7 seconds are probably enough to quickly get away from the saber-toothed cat, or to move out of the road when you are walking on the M2, right? That's enough. But anything longer than 7 seconds, you don't have the energy. But then, surely, Lizzie does 200 meter, yeah? And even Usain Bolt needs another energy resource. Where does this energy come from? Basically, the energy comes from stored compounds in the muscles, and the storage form that the muscles predominantly use is the stored form of glucose. When you put lots and lots and lots of glucose together, it's not just a lump of sugar. You modify this so that it is still soluble, but it can be easily used, and where the individual sugar molecules are connected to each other. And what you get when you do that is a compound called glycogen. Glycogen are thousands of glucose molecules attached to each other, and the bond goes via 1,4. What on earth does that mean? Let's very schematically draw a glucose molecule. That is my glucose molecule. The dark dots are carbon. And I honestly can't be bothered to put in the OH groups because I always get it wrong, which way is sticking up, which way is sticking down. So I just draw glucose like that. We have 1, 2, 3, 4, 5, 6 glucose molecules. That is position 1, 2, 3, 4, 5, and 6. These are the glucose molecules. And in glycogen, we basically have a bond. Let me do that nicely. Which is a glycosidic bond between position 1 and position 4 of the different glucose molecules. And you have got 1, 4, 1, 4, 1, 4, 1, 4, 1, 4, 1,000 times. And occasionally, you also have a 1,6 bond. And what does that do to your glycogen chain is basically you have a long chain, and here you've got a 1,6 as well. Oh, I can't. You can draw that, you can, So you have a highly complex molecule which is branched. So you've got branch points. So here's a branch point, here's a branch point, here, And wherever you have a branch point, you have not only a 1,4, but you also have 1,6 connection. Make sense? Glycogen is the source of energy, and as soon as your cell or our cells run out of ATP, we activate a mechanism that removes the glucose from glycogen. Glycogen, these highly branched molecules are usually in little sort of, if you like, bodies or little clumps, in little clusters. And I compare it to sugar lumps. And there is then one particular enzyme that sits there and that chops off this 1,4 bond. It cuts this 1,4 bond and releases glucose. This reaction is catalyzed by an absolutely essential enzyme. This enzyme is actually called glycogen phosphorylase. And we will talk about this enzyme a little bit more when we talk about regulation of how things actually work. Now, what does this enzyme actually do? As I said, it cuts the bond here. This bond here. And we already know that very often when we cut a bond, we use water to cut that bond. And this reaction would be called a hydrolytic reaction. Hydrolytic, because we use water to break lytic the bond. In this case, that is not how it happens. We do not use water in this case. Instead, what we use is, instead of water, we use phosphate. We use a phosphate group. And this phosphate group gets attached to the 1 position. So this thing would be called glucose 1 phosphate. And this is basically the starting point for a lot of subsequent reactions. There is then another enzyme that converts this glucose 1 phosphate into this guy. And of course, you would call that, what is that? This one here now?
Glucose 6-phosphate?
It is absolutely right, Oscar. It's glucose 6-phosphate, right? So, or lovingly known as G6P, glucose 6-phosphate. Now, why on earth do we use phosphate and not just water? What would happen if we just use water? What do you reckon in this case? Instead of phosphate, what would we get? Just water. Not necessarily, because this reaction is sets free some energy. So it would not go back. But what compound would we get if we just use water? Glucose. Yeah? We would get immediately glucose. But there's energy stored in this 1,4 bond. So if we just simply add water, we would waste this energy. But if we add a phosphate group, in a way, we conserve this energy in this bond. And we then later can use this phosphate bond to transfer the phosphate onto, for example, ATP, and make use of it, of this energy. So water would just simply waste the energy. Phosphate, in this case, preserves the energy. There's also a second reason why we add a phosphate group to glucose. Remember, we are in the cell. Glucose, how does glucose actually get into a cell? Let's say you have your Mars bar, lots of sugar. Sugar is broken down in the mouth with enzymes, gets into the intestine. From the intestine, it gets into the blood, and the blood supplies all the cells. How does glucose get into the cell? Diffusion? Yes and no. Think about it. Glucose is, what is it? Is it polar molecule? Is it apolar? Is it lipophilic? Is it hydrophobic? What do you reckon? Remember, it has lots of OH groups. So we would expect it to be fairly polar. Now, does a polar substance easily get through a membrane? But it goes no. So what we have here, each cell has transporters. And it is, if you like, facilitated diffusion. But you need a transporter in order to get through the membrane. So that's how glucose gets into a cell. But that's also how glucose gets out of a cell. Now, of course, we don't want the glucose that we just put into the cell, we don't want it to just at the other end come out again. That would be pretty stupid. So the cell uses a trick because the transporters accept glucose but have no interest whatsoever in phosphorylated glucose. So, transport of glucose. Yep. Transport of glucose phosphate. No. So by phosphorylating our glucose, we trap the glucose inside the cell. Can't get out. Really, only liver cells send glucose back out, but we will discuss that a little bit later. Does that make sense? So we need to trap the glucose inside. What happens next with the glucose? As I said, when it comes from glycogen, we convert it from glucose 1-phosphate to glucose 6-phosphate. And the enzyme that does that, a little hint for one of the quizzes, this enzyme is called phosphoglucomutase. Just simply because mutase shifts the phosphate group from the 1 position into the 6th position. And glucose 6-phosphate is really sort of the Trafalgar Square of the metabolism. This is where everything comes together and everything goes out again. Glucose 6-phosphate is one of the central metabolites in any cell. Exactly. Now, we have now glucose, and if glucose comes in through a transporter, it's not phosphorylated. Only when we use the glycogen, our sugar stores, then the glucose is phosphorylated. But if it just comes in through the transporters, we basically have this situation. Are you happy with me drawing glucose like that? Yeah? Because as I say, I can't remember which way is up, which way is down, and all this crap. So that's glucose, that's in the cell, and we immediately, when it comes in, we have to phosphorylate it. And what we do is we use ATP to phosphorylate glucose. And this time we don't need to do the bypass. We immediately phosphorylate the glucose in the 6th position. So we get glucose 6-phosphate. The enzyme that we use for that you can almost figure out what the name for that is. It uses a hexose. Hexose means 6 sugars, 6 carbons in the sugar, and it transfers a phosphate residue, so it's a kinase. So this guy is called hexokinase. Hexokinase in the cell phosphorylates the glucose, traps it. This step actually is one of the key steps of the breakdown of glucose. Because what we are going to do is we use the glucose to generate energy, to generate ATP. In the next step, from this glucose 6-phosphate, we shift it a little bit around with the enzyme glucose 6-phosphate isomerase. And what we get is ECH. This molecule. So you see it's no longer a 6-ring, it's now a 5-ring. Or in other words, while in glucose the ring oxygen comes from the aldehyde, in this molecule the ring oxygen comes from a keto group. Any ideas what this is? Fructose, thank you. And which one? Thank you. So that is fructose 6-phosphate. Again, key reaction. But the next one is even more important. We take this fructose 6-phosphate, and I probably should draw it like that. Glucose 6-phosphate isomerase, this reaction is reversible. The hexokinase reaction is almost irreversible. The next step, from fructose 6-phosphate, the next step is also irreversible. We use another molecule of ATP, and convert fructose 6-phosphate into this molecule. What would you call that? It now has 2 phosphates. Katie? I love it. Thank you very much, because you played a beautiful ball into my court. This molecule is called fructose 1, 6, and now here it comes. Bisphosphate. Why is it not, as you suggested, diphosphate? Diphosphate means the two phosphates are linked together, like in ADP. That's where both phosphates are linked together. That's di. Bis means twice. We have the phosphate group twice, but they are not linked together. Make sense? Here, the enzyme that does that, again, you probably can already figure out what this enzyme is called. It's called phosphofructokinase. Phosphofructokinase. And because life isn't complicated enough, this thing is phosphofructokinase 1. Or abbreviated as PFK. PFK1. Why am I harping on about that? Because there is another fructokinase, which we will discuss as well, PFK2, phosphofructokinase 2, which does a similar reaction, which is totally different. Because it generates a different fructose molecule with two phosphates, but in different places. But we need that. Right, so we have fructose 1,6-bisphosphate, or abbreviated as F16BP. And now we are ready to do some fancy stuff. What we do with this is we actually split the fructose 1,6-bisphosphate in two portions. Oops, and I did it exactly wrong. The enzyme that does that is called an aldolase. Not necessarily intuitive, but, well. Simply because the two products can come together again and form an aldol reaction. Don't worry too much about it. What we get from this reaction is we get two products. One product, and both products, I want to point out, both products are phosphorylated. One product is, how do I write that? Is this guy, and the other one is this guy. This one here is called dihydroxy. dihydroxyacetone phosphate. I hope you understand acetone. Do you spell it with an E? I think so, yeah. In future, phosphate, I always abbreviate with P with a ring around it. That indicates phosphate. Dihydroxyacetone phosphate. And this guy here, what functional group do you see in this molecule on your left here? What does it have? It has a phosphate group. Sorry? It has an aldehyde. Exactly. We have an aldehyde, and of course we have an OH group. And therefore this guy is called glyceraldehyde. And if I could spell, (3-phosphate). Both compounds can very easily be converted into each other. So there is a very easy reversible reaction, which is performed by my friend Tim. Hi, Timmy. Which stands for triose isomerase. Why it's an M, I don't know. Just somebody called it Tim. And it's a reversible process. Right, so what can we do with this glycerol aldehyde 3-phosphate? And that actually is the one where we move on with. An aldehyde, is it stable or not very stable? What do you reckon? Aldehyde stable, not stable? What's your stable? It's stable? It is stable, but actually it's not terribly stable. It wants to either become reduced to an alcohol or oxidized to an acid. So an aldehyde actually contains energy. And what we want to do is we want to conserve this energy. What we do is we oxidize this guy, glycerol aldehyde 3-phosphate, and we add a phosphate. And what we get is this molecule here. It's no longer an aldehyde. It's actually an acid. And therefore it's called 1,3. No, sorry. It is glycerate 1,3. Is it di or bis? It's bis. Thank you. Because they are not connected. Glycerate 1,3 bisphosphate. The enzyme for that is, where do I write that? Glyceraldehyde 3 phosphate dehydrogenase. And if you've counted, we lost some electrons. No, we lost some hydrogens. We gained some electrons. So what happened to the hydrogens? Actually, we use these hydrogens to produce NADH. We put in NAD plus, I should say, and we get NADH H plus. Usually people just simply write NADH. So this NADH that we get here, if you like, has the reducing equivalence. It is a liquid, how shall I say, liquid hydrogen transporter in the cell. And we know from, I think, Dr. Beale's lecture last week, you did that? No, the week before, week 18, where NADH goes into the mitochondria and produces ATP. True? How much ATP per NADH? So the textbooks before 1990 gave 3 mole ATP per mole NADH in the mitochondria, but unfortunately this has been corrected and this is now more 2.5 mole ATP per mole NADH. So by generating this NADH, we have something that potentially gives us ATP. The problem is we need to get this into the mitochondria, because what I have described here so far all happens in the cytosol of the cell. There are no other organelles involved, only the cytosol or cytoplasm. How we get the NADH into the mitochondria, I tell you in a different, at a different point. What we can do now with our glycerol 1,3-bisphosphate is we can remove the first phosphate we transfer this phosphate onto ADP. And we shift things a little bit around. And we get another high energy compound. There are a few steps in between, but I don't bore you with that. So we've transferred basically the top phosphate from the 1 position onto ATP, and we shifted the phosphate in the lower position into the 2 position. This guy is called phosphoenol pyruvate, or PEP. Please don't call it Guardiola. Has nothing to do with the football manager. The only connection is that they are both called Pep. But yeah, don't worry, forget it. The enzyme that does this reaction is called phosphoglycerate kinase. Again, kinase because we transfer a phosphate group onto something else. Now, I don't know what you have done with my colleague, Dr. Beal, but I do know that he taught you about ATP generation. Is that right? You did ATP generation in the mitochondria, and he told you that in the mitochondria you use oxygen, and this kind of ATP generation is called oxidative phosphorylation in the mitochondria. Yeah? Here we generate ATP but without any oxygen involved. What we use actually is a substrate here. And therefore, this ATP generation is called substrate level phosphorylation, which is totally different to the oxidative phosphorylation in the mitochondria. In order to generate ATP here, we do not need mitochondria. And in fact, this process is actually used by cells that do not have mitochondria. Wait a moment. Are there any cells that don't have mitochondria? In your body? Red blood cells, absolutely right. Red blood cells, they are sort of the poor sods. They don't have a nucleus, they don't have mitochondria, but they have the enzymes for this process. So substrate level phosphorylation. And because it was so much fun, and we are very short, we are going to have to break short in just a minute or so. Because it was so much fun, we do the same thing, substrate level phosphorylation again, from this guy here. ADP to ATP. And we transfer the phosphate group again onto ATP. And we end up with this molecule. And you have seen that before, and you have worked with that, because that was the thing in the practical. It's pyruvate. And I particularly like this enzyme because this reaction is done by the enzyme pyruvate kinase, or as it is known as PK. Guess why I like this enzyme? this is actually the reaction of what is generally known as glycolysis. Glycolysis ends with pyruvate. We have a 5-minute break, and then we sort of sum it up a little bit, what we gain through glycolysis. Back in 5, okay?
I managed to submit it on time, but I submitted a second copy after my partner pointed out some problems. I just want to know if that was okay to resubmit it. I wrote a note that was a resubmission.
What's your name?
April,
What's your login?
AA 22
52.
2253.
53.
Yeah.
And what's the problem again?
So I submitted a first copy, then a second copy, which was like correcting some issues that I
Okay.
had. I wrote on the second copy.
Okay.
That's
So I will find it.
yeah.
No problem.
Thank you.
Hello. When so you were saying that you've got right at the beginning of all of that, there was the one that made fructose 1.
So you are going from, so you produce fructose 6-phosphate.
Yeah, but do you produce that directly from glucose?
Yes.
So what was the other stuff where you put it on carbon 1 first and then onto carbon 6?
Oh, if you, right. So if you are coming from glycogen,
Yeah.
you add the phosphate to the 1 position.
Right.
Yeah? If you don't come from glucose,
okay.
from glycogen, you add the phosphate to the 6th
So
position.
if you just come in directly from
Yeah.
glucose. Perfect.
Yeah?
Yep.
And you convert the 1-phosphate into the 6-phosphate, and from the 6-phosphate it goes to fructose.
Yeah. So hexokinase
Hexokinase,
is a different enzyme to the ones that
glycogen phosphorylase.
Yeah.
Totally different.
Totally different. Okay, perfect. Thank
Yeah.
you.
Yeah, that answers some of my questions at least.
Mhm.
But I think I missed an enzyme here from glycerol
Oh, yes.
aldehyde 3P to glycerate 1,3 bis.
So this is glycerol aldehyde. I think I've got it here.
yeah, it was
Glycerol
yeah,
aldehyde 3-phosphate.
it was this one.
This
yeah.
one. Glycerol aldehyde 3-phosphate dehydrogenase,
Okay.
or just simply GAPDH.
Yeah. Glycerol aldehyde.
Yeah.
I just couldn't read
Because
what
that
you
is
written.
the glycerol aldehyde that you have there.
Yeah.
Make sense?
Yeah, glycerol aldehyde.
3-phosphate
Yeah, dehydrogenase.
dehydrogenase.
Okay, thank you. And yeah, what was
Tim.
that? An enzyme?
Triose isomerase.
Yeah, okay. Maybe not that important at the moment, so.
It's not terribly important. I will point out the important enzymes
Yeah.
that we are going to discuss for regulation.
Okay, thank you.
Pleasure. Be back in 3. Yeah. Does it make sense? Does the stuff you have done that
all in the cytosol?
So it's all in the cytosol. Yeah. You've done that before.
I mean, it's just kind of a slightly more in-depth. Yeah.
This is in depth.
I mean,
Good Lord, you should see the slides that Rokas has given me with the detailed mechanism and the binding sites of
no,
the.
I'm saying like compared to like A level, it's just like adding
Yeah.
a little bit more.
Okay, good.
It's not that.
It's not that interesting. Is that what you mean?
No.
That's fine. It's absolutely. Look, I don't take it personally.
It's not you. It's just that I'm so tired.
Do I ask why you are tired, or is that just because you're tired? It's not.
It's just like
I don't think I've ever
14
seen.
kilometers this afternoon.
So why are you tired now?
I know. It's like the stress.
You're probably the tiredest person I've met my whole life. You're like always tired all the time.
It's because I have insomnia.
What time is it today?
Really?
Yeah.
I'm surprised, because at your age, you shouldn't have insomnia.
Oh, you should. I've had insomnia since I was a baby. Literally never slept.
Ever in a whole life. It's getting pretty dangerous now. They're
Yeah.
worried about it.
I actually like never.
19
had a
years of not sleeping.
Have you had checks?
Yeah.
Thyroid?
Yeah.
It's all good.
Yeah.
Fair enough. Fair enough. You have done that in A level? No? A 3-step version. Good Lord, how do you do that in 3 steps? Okay. So at least there's a little bit of new stuff. Because I don't want to bore people, but you haven't done that at all. on, guys?
We're coming.
Good. I'm pleased to hear that.
Just about to go in.
You're what? Okay, shall we continue? You've replenished the glycogen. You're full of glucose now. Fantastic. Please don't forget attendance monitoring round 2. And by the way, it says on my timetable that on Monday we have a test. Is that right? No, we don't. Because this test has been replaced with the online quizzes. But we still have a lecture on Monday. I use this slot for the quiz, for the test, to expand a little bit on further regulation of these things. So please come to the teaching session or watch it on the live stream. Okay? Right. Now, we did the glycolysis in moderate detail. Had you done this with my colleague last year, you would have had a look at the details of the reaction mechanisms for each step, at the active sites at each step, and at the energetics at each step. And by the end, you probably would think that you are a banana tree. But I'm not going to do that with you. This life is too short. But let's have a quick look at the summary of glycolysis. So we start with glucose here. And we add 2 ATPs in order to get to the fructose 1,6-bisphosphate, to this point here. And this step up to here, this is called the preparatory phase. That's the prep phase, where we, in a way, we prepare the glucose so that it becomes useful. A couple of years ago, a student sold it to me as the foreplay phase in an exam. Yes, I can see where they are coming from, but maybe not. In some textbooks, then you find that you have another phase, which is what is called the split phase, where you just simply split the fructose 1,6-bisphosphate. And you then have basically everything double. So when we said we produce an ATP here in one of the steps, it's actually we produce, per molecule of glucose, we produce 2 ATPs because we have got these 2 fragments, the dihydroxyacetone phosphate and the glycerol aldehyde 3-phosphate. So we have these 2, and usually it's only written as 1, but implicitly it means we have 2 things. So we have got 2 3-carbon bodies. And therefore what we get is, I actually did the arrows wrong. What we get out is 4 ATPs per molecule of glucose, and 2 molecules of NADH. So our sort of balance sheet would look like glucose plus 2 ATP gives us 2 pyruvate plus 4 ATP plus 2 NADH. We need the 2 ATP to get the glucose ready, but then we get 4 ATP out of it. So net, we would get basically 2 ATP out of it. So you can also write this as glucose. 2 pyruvate plus 2 ATP plus 2 NADH. And of course, we get some energy out of it, out of this process. And the standard delta G naught prime for this reaction is negative 85 kilojoule per mole. And this hook thing, that is my way of writing joule. It's not a square bracket. Yeah? Good, thank you. Because we get some, actually I can't remember what precisely the delta G for that is, but it's also negative, this reaction goes through. But it's not a lot of energy that we get from that, unfortunately. For each molecule of glucose that we burn, we get 2 ATPs. And I think I told you, under physiological conditions, 1 ATP, when we hydrolyze it, anorganic phosphate, we get in the cell, under physiological condition, we get a delta G of around negative 50 to negative 70 kilojoule per mole. And that's actually a very useful value, which you probably find useful for one of the quizzes and for the multiple choice questions in the exam. Oops, I shouldn't have said that. So we are not really getting a lot out of this burning glucose. But then on the other hand, glucose is full of energy. So where's the remaining energy? Where did it go? Well, actually, the energy is still located in pyruvate. Pyruvate is still a high energy compound. We've just utilized a small fraction. And of course, we get a little bit of, we get some NADH, which we can transport into the mitochondria. And depending on which cell type we are looking there are 2 different ways of getting NADH into mitochondria, because we are still in the cytosol. And we really, in order to produce ATP through oxidative phosphorylation, we need to get the NADH into the mitochondria. And there is what is called the malate aspartate shuttle. and the glycerol I think phosphate. These are shuttles that transport the NADH into the mitochondria, where the mitochondria use the NADH to produce ATP. I'm not going into detail for these shuttles. You can look them up. I'm not going to ask any particular details about these shuttles in any test or exams. But it's quite useful to know because there is a fundamental difference. The malate aspartate shuttle transports actually NADH from the cytosol into the mitochondria. The glycerol shuttle is less efficient. It takes NADH but delivers only FADH. And from the lecture from Dave, you know that FADH produces less ATP than NADH. It's sort of, in the glycerol shuttle, it takes a little bit of a cut. Give me your energy. Okay, so we also have a slight problem when we look at the overall equation for glycolysis, because we don't get a lot of ATP out. So if we want to sustain running away from the saber-toothed cat or do a 200, 400, 10K or marathon, we very quickly would have burned all our ATP within the first 5 to 7 seconds, and then we burn all the glucose and don't get a lot out of it. Just get 2 lousy ATPs out of it. And another problem is we accumulate NADH. Now the transport of NADH into the mitochondria is slow. It's really slow process compared to the other reactions. So we are sitting there, we've got lots of NADH in the muscle cell. What the heck are we going to do? Because if we don't have NAD for this step here, let's see if I can find a blue. Oh yes, blue, I like blue. For this step here, if we don't have NAD here in this step, the whole process comes to a standstill. And there's only a very small concentration of NAD present. So very soon, we basically hit the glass ceiling. We cannot carry on with the glycolysis, not because we run out of sugar. Sugar is plenty. Glycogen is plenty there. Actually, the biggest glycogen stores in the body, where do you think they are? Glycogen. Where is glycogen stored? Which organs? Liver and muscle, exactly. Which one has more? Liver. You see, there was a trick question. You are absolutely right. Liver has more glycogen when you compare it to the mass of the liver. So about, I think, 30% of the liver weight can be glycogen. But because your muscle weight is so much higher, actually it turns out that muscle, overall, if you add them all up, the muscle and the glycogen, the muscle, the skeletal muscle, has overall the highest amount of glycogen. So, but glycogen, in principle, liver and skeletal muscle. And it will last, the glycogen stores will last realistically, if you don't replenish it with any other way, will last you for a day. So if you don't eat anything and no other mechanisms kick in, within, say, 16 to 24 hours, your glycogen stores go down. And pretty much that's it. What do you do in order to reload? Sports people? You do? Glycogen loading is actually a term, glycogen loading, where you try to put in as much useful glucose so that you replenish the glycogen stores. When you do the interval fasting, where you go on a diet and don't eat for a day, what you basically do is you lower your glycogen stores, because then your body is forced to switch to other fuels, like burning of fatty acids. Which organ actually uses the most glucose in your body? It is indeed. It's the brain. And the brain uses up to 75% of the glucose that is in your body. Unless you are a politician. Damn it, I shouldn't have said that, right? So you guys out there, please forget that. You know, I'm not dissing politicians. I think everybody should have one. Okay, so we still have the problem. We have NADH there. We have accumulated NADH, and this NADH is sitting there in the glycosol, and if we don't get rid of the NADH, PDQ, which stands for pretty damn quickly, our glycolysis comes to a standstill. What can we do in order to get rid of the NADH? We can oxidize it back to NAD, absolutely right. So we need to actually transfer the hydrogens that we have in the NADH. We need to transfer them onto a different substrate. What we can do, and you all have done this experiment, you take pyruvate, and you transfer the hydrogens, and what do you get? Gave you the clue. You have done that. You transfer the NADH, the hydrogens, you transfer that onto pyruvate and you get lactate. And this is the stuff that bloody hurts when you do exercise. It's the lactate in your muscle that gives you the pain. Because lactate is a much stronger acid than pyruvate. So the muscle gets too acidic, and that is what hurts. So we've got NAD back, so we can run glycolysis. But we have another problem. We now have lactate sitting there. God damn it. What do we do with the lactate in the muscle? Where does the lactate go? What can we do with it? Actually, what we can do is, from our muscle, I hope you are reasonably impressed with my drawing skills. Where we have lots of lactate now. What we can do is we can transport the lactate oh dear. Good, this peanut is supposed to be the liver. We can transport the lactate to the liver. In the liver is sort of the all-rounder of all the organs. We convert the lactate back to pyruvate. And send the pyruvate back to the muscle. It is sort of, if you like, a temporary detox. Get rid of the lactate in the muscle where it does damage, recycle it, but still in the liver we need, again, NAD+, but the liver has a much higher pool of NAD+ compared to the muscle. This cycle is actually called the Cori cycle. And it happens all the time. When you do a little bit of exercise, lactate is produced in your muscle, and the lactate is transferred to the liver through the blood. In the liver, you regenerate pyruvate, and that goes back to the muscle. Make sense? Right. So far, so good. Now, obviously, what we need to do is this glycolysis, and with this lactate stuff, you probably noticed we need to be really aware what we are doing here. We need to regulate things. Without regulation, you are, what is the term? The technical term, royally screwed. If things don't get properly regulated, you aren't going to survive. Now, glycolysis has basically 3 steps that are more or less irreversible and that are highly regulated. The first step, which is basically more or less irreversible, is this one, from glucose to glucose 6-phosphate. And I told you it is catalyzed by hexokinase, and we need ATP. And here's something really interesting in terms of a regulatory mechanism. Because you not only have one type of hexokinase in your body expressed, you actually have 4 what is called isoenzymes. Now, what the heck is an isoenzyme? An isoenzyme is an enzyme or is a protein that differs from the other isoenzyme. So the enzymes catalyze the same reaction, probably have the same substrates, but these 4 different isoenzymes have slightly different amino acid chains. So what you have basically is you have hexokinase 1, 2, and 3. They are all pretty similar, but they have different, they have changes in the amino acid chain. How do you get these changes? Just simply you have the same gene for them. You do splicing. You heard about splicing? You've done splicing, yeah? Where you just simply take the mRNA and cut out different exons. Well, you cut out the introns, and sometimes you have differential splicing, so you get different amino acids, different amino acid chains for the different isoenzymes. These are referred as the standard hexokinases. And what they have, what they show is they grab glucose and whack on the ATP onto the 6-phosphate, onto the 6th position. And usually the Km of these isoenzymes is around 0.1 millimolar for glucose. We know Km gives us a measure of the affinity of the hexokinases to glucose. So at a concentration, at a glucose concentration of 0.1 millimolar, we have half saturation, half maximum velocity of hexokinase 1, 2, 3. Usually, in the blood, you have, depending on whether you have recently eaten or not, but usually your blood glucose level is maintained at around 4.5 millimolar. So what we see is that Km is much, much lower than the blood level of glucose, which means our hexokinases 1, 2, 3 are basically always working with full speed. So this means HK1, 2, 3, always working close to Vmax. So if we draw do, say, activity. And we have glucose concentration. What we would find for hexokinases, let's say here we've got 10 millimolar, here we've got 5 millimolar. Our hexokinase 1, 2, 3 are basically like this. As soon as glucose comes into the cell, it will be phosphorylated, so it can't get out again. Yep. And you probably noticed I spoke about 4 isoenzymes, and I've just got 3 here, because hexokinase 4, and very often it is not referred to as hexokinase, it is referred to as glucokinase. Glucokinase is very different. It still catalyzes the reaction of glucose plus ATP gives glucose 6-phosphate. But Km for glucokinase is in the range of 10 millimolar. And actually, if you give it something lower than 10 millimolar, not a lot happens. And if you do a plot for glucokinase, what you will find is something like that. So that is glucokinase, or hexokinase 4. Sometimes people just simply say hexokinase when they mean hexokinase 1, 2, 3, and glucokinase when they mean hexokinase 4. So be aware of that. So when you see something with hexokinase only, without any addition, then it usually means hexokinase 1, 2, 3. Now that is weird. It shows a sigmoidal curve, an S curve. Hexokinase 1, 2, 3 are usually expressed in almost all cells that you have, with one exception, or few exceptions. You won't find hexokinase 1, 2, 3, or I just simply call them hexokinase. You won't find hexokinase in the liver. Instead, in the liver, you only find glucokinase. Actually, that's a much nicer liver than I've drawn before. So glucokinase is in the liver. And why is that important? Because the liver actually regulates how much glucose should be in the blood. In the liver, you have sort of a sensor mechanism. And this sensor is actually glucokinase. So, what happens? You have a skeletal muscle, glucose comes in, the muscle says, hey, cool, yes, something to eat. I want food. I won't let this go out. I phosphorylate it with my hexokinases. There's no way this stuff can go out. Only as lactate, but it comes back as pyruvate. In the liver says, well, glucose comes in, great, I keep it in. But if somebody else needs glucose, I provide the glucose and send it out again. Same happens with the glycogen in the liver. If somebody says, hey, I need sugar, give me sugar, sugar baby, then the liver will produce the sugar, will take the glycogen from its own store. It's really unselfish, isn't it? And deliver it to the bloodstream where it can get to the right organ. So, had the liver only hexokinases in it, it would immediately phosphorylate all the glucose that's in the liver, and it would not be able to regulate how much glucose is swimming around in the blood. But the liver doesn't have the hexokinase, it only has the glucokinase. And if the concentration of glucose in the liver is fairly low, then the glucokinase will not work properly. It will not trap the glucose in the liver. Only when the concentration is very high, so in this range here, let me change the color, only if we are in this range here, the liver says, all right, there is so much glucose swimming around, I can actually use the glucose to build up glycogen stores, and I don't have to worry in subsidizing somebody else with the glucose. So there is enough glucose there. So glucokinase is a fantastic sensor. Does that make sense? Yeah? Now, what we see here is a very nice mechanism of regulation. Different organs, different cells actually express different enzymes depending on the cell type with slightly different function. And in a way, it makes sense. The glucose is the glucostat of the body. It provides everybody else with glucose if required. So that is one very important sort of regulatory mechanism. We have differential expression of enzymes in different cells, or we can go even further. We can have differential expression and existence of different enzymes in different compartments. So, for example, all the enzymes for glycolysis are exclusively in the cytosol. All the enzymes for oxidative phosphorylation are in the mitochondria. If you mix these two things, you're totally effed. So, in terms of regulation, different organs, different cell compartments. And of course, you have to make sure that the different enzymes go into the right compartments. And how you do that, you have discussed, I think, with Dr. Mansfield, with all the signal sequences and things like that. So I better stop at that point. So, does it make sense? On Monday, We will look a little bit into more regulations, because that's not the whole story with hexokinase. See you on Monday. No, see you tomorrow for the BI308. Thank you very much.